All right, so last time we spoke about some quantum aspects, and the most important amongst which was this operator product expansion. This OP, was a statement about what happens when you bring two local operators close to each other, and we said that it can be approximated by a string of operators at one of the points, and this was the form of the OP that we wrote down. And so here theseCijks are functions, and we said that they were of this form because there was translational invariance. The important thing was that this OPE was to be understood as something which makes sense inside endpoint functions, and we had various other comments regarding this, about the fact that the OPE actually, since it's inside these endpoint functions, and these endpoint functions themselves, come with some particular ordering. So you could take OI and OJ through each other, and these will actually, inside this, in the form of the OPE, they're going to just commute, since, as I said, right now ordering was already taken into account in these endpoint functions. So that was one, and we also said, I didn't prove this, we're not going to prove this, but we'll say a few more things about this later as well. So I'm sorry, just give me a sec. Yeah, okay, yeah. So and we said that the radius of convergence of these OPs would actually be equal to the distance of the next nearest insertion. And the only thing that you need to take care about the other operator insertions was the fact that they should be at distances larger compared to the distance between these two operators, of which we are trying to look at the OPE. So it has to be a large compared to the modulus of z minus omega, where your two operators O1 and O2 are inserted at z and omega. Okay. These OPs, as we saw, will have singular behavior when z goes to omega, and this is essentially the only thing that we are going to actually care about. And the non-singular terms will just be written with some dots. Okay. And what will happen is that the singular terms will contain the same amount of information as, say, the commutator relations, for example. Then we went on to trying to understand word identities, and word identities were word identities were sort of the quantum mechanical analog of Noether's theorem, and there what we did is we started off with a path integral, and arrived at the form of so what the change in the path integral would be when we were to promote these small parameter epsilon to epsilon x. We saw that the path integral gets shifted to something like this, and then by the virtue of the fact that the path integral has to stay the same, since it was just a redefinition of this integration variable phi, we put this guy equal to 0, and And what we saw is that so this essentially was equivalent to del alpha j alpha equal to 0. So this was an operator statement. So this was a quantum version, if you wish, of Noether's theorem. What we saw is you could even do more. Instead of looking at the path integral, you could now look at endpoint functions, and you could have, I mean, endpoint uh, uh, functions where these operator insertions either did not have support in the region where epsilon was non-zero, or had an insertion where I mean epsilon was non-zero. So the first case was sort of very very similar to what we did just for the partition function, and then everything just went through, and again we had del alpha j alpha equal to 0 through as an operator equation. Okay, so that was where we were looking at the first case. There were no sort of operator insertions where this epsilon was not zero. But on the other hand, when we looked at something where there were some insertions at the same point as J alpha, equivalently, we asked what happens when X approaches one of these insertion points. Then we saw that there is going to be, so we saw that we had an expression of these endpoint functions with this j insertions in them, and we got an identity which looked like this, and this was what was our ward identity. Okay, so this is something that we found last time around, and this was sort of the principal result that we had from last time around. Okay. What I said was 3.17. This particular thing was true for all sort of field theories. Now, what we are going to be doing, we are going to be interested in the case where the symmetry in question is conformal invariance in D equal to 2. Okay. So that's what we want to do now. So what we want to do is, essentially, we want to bring what we did in the first half of the class and what we did in the second half of the class, and find some expression for what is going to be the conformal ward identity. Okay, so any questions so far from the last class? All right, if not, let me just go ahead and let's just first briefly see something that is related to the stress tensor, because this is something that we're going to be using a lot. So you remember that the stress tensor T alpha beta would provide the Noether currents for translational symmetry. But let's look at let's look at the other ones, and let's look at the infinitesimal change of z prime goes to z plus epsilon z, and z bar prime goes to z bar plus epsilon bar z bar. So again, what do we do? So we need to promote epsilon to be dependent on position. But since epsilon already depends on z, what this amounts to is just taking epsilon to some z of z bar. Okay, let's look at the change. So you know that delta s in this case is going to be given. So we are looking at a change in G alpha beta. So let's call, so we are in 2 dimensions. I'll this is sigma. So delta s is del G alpha beta and delta G alpha beta. This, as you know, is just T alpha beta up to some coefficients in front, and then we have G alpha beta, right? Now again, you will remember when we are looking at infinitesimal changes in G alpha beta, this is just written as del alpha epsilon beta plus del beta epsilon alpha. And what we will do, this I mean change that we have, so that's just the infinitesimal changes. We said that we are going to look at these guys. So del sigma alpha is just epsilon alpha, right? So we put these back. So we put these expressions back here. So what you get is so what you end up with is T alpha beta, which was here, and now uh, del alpha of G alpha beta upstairs, it just takes this form, right? So this is something that we have, you have also used the fact that, the alpha beta is, so you have also symmetrized it. So just keep that in mind, okay? So if you write this in sort of Z and Z bar, then what happens is what you end up with is that you can expand this out, and then this just becomes TZZ del Z of uh, delta Z, and TZZ bar delta Z bar of del Z bar. As you can see, I've used the fact that TZZ bar is equal to 0. That is what we have used here, and these are so we have used this, and this is why this is a conformal transformation, because the stress tensor is traceless, and so you don't have a ZZ bar piece. So delta S in that case just amounts to saying that this is equal to this. Okay. So that is what we have. So so now if you see, so if you have epsilon is holomorphic and epsilon bar is anti-holomorphic, then we just immediately see that delta is equal to 0. This is of course the fact that we have a symmetry, right? Now let's at this stage use the trick of treating Z and Z bar as independent, and look separately at some J alphas that we'll be getting from shifts of Z and Z bar. Okay, this is rather straightforward, so let's just do this. So what we will do is we will take del Z as epsilon Z, and del Z bar is 0. So now so what we can do is we can just use this particular expression that we have out here, and just read off what the J alphas would be in this case, right? So we will use this standard trick of letting the small parameter depend on position. As we said, this means that you are promoting epsilon Z to some epsilon of Z bar, and that essentially means that you have to multiply this thing by some f of Z bar. Okay. And once we do that, we are going to look at some function for some function f, and we are going to look at the del f term. I'll leave it for, this is a rather straightforward exercise, so I'll just leave it for you guys to do. So at the end of the day, what happens is that you have something which is j. So J of Z upstairs is equal to 0, and J of Z bar upstairs gives you TZ of epsilon Z. Just remember the fact that J of Z. Okay. Let me just remind you of something that so what you have is J. If you had something like GZZ, this actually is going to be equal to 0. GZ bar Z bar is going to be equal to 0, and the only thing that is non-zero is GZZ bar, right? So if you just write G, which is just a diagonal matrix in this form, I forget if this is a 2 or a half, but I think it's a 2. So this is just what you're doing is just you're writing eta mu nu, which was just 1 0 0 1 in a form which is where you take things in z bar. So G, so if you wish, this in this z bar coordinate system just transforms into something like 0 2 2 0, I guess. So I mean I'm a little unsure about the factors of 2, so we we can just look this up somewhere else. So what I mean, the reason why I try to say this, is the fact that so what you get out here is J. So what you will have is J mu, if you wish, is JZ and JZ bar. So this gives you, so this is 1, and then you'll also get something like J bar mu, if you wish. So this is going to be J bar Z, J bar Z bar. Okay. So these are two things that you're going to get. I mean, so J mu gives you this one, and J bar mu is going to give you something like that. So let's get rid of these things now. So the upshot is that you are going to get, so J has an expression which looks like this. The important part is, J of Z bar is something that looks like TZ epsilon Z. So as you know, so this is this J is itself going to be holomorphic guy, because this does not have any Z bar dependence. So you already know that J del alpha J alpha is equal to 0. So this particular identity holds. But you also now have seen that this particular thing is equal to 0. Okay. I am getting, yes. So this is also equal to 0. Okay. So you need to keep this in mind. Very good. So you can similarly look at the anti-holomorphic piece, and then you're going to find that so you're also going to get something. So what have we done? We have just said, we've just looked at what the I mean J alphas which will correspond to shifts of Z will look like, and we have found some expressions for them. All right. So we are going to use this, just in the next little bit. But now let's come back to the analysis of word identities. Okay. Now remember that we had an integration where we were going to go around a circle here. So that essentially, so let me just take you back here. So what happens is that you have these insertions, right? So we have to go around this circle, which was epsilon of Z. So this is an integral that you need to do. Okay. So in 2 dimensions, what's the nice thing? So this is again something that is going to be reasonably straightforward and familiar to you from earlier. So what we do is we take del alpha J alpha, and we use Stokes theorem, right? So if you use Stokes theorem, then this just becomes an integration over the boundary. And now it's J1 d sigma 2 minus J2 d sigma 1. Remember that this essentially looks like integral of, so this is something that you are eminently familiar with from your math methods, the things that you have done earlier. So in your two-dimensional case, what is going to happen is that you can use Stokes theorem to move this into something like this. Okay. Now, so now you transfer from some 1, 2 to the ZZ bar coordinates, and you're going to pick a sign and an I up. And once you do this, what you want to do is you want to plug this into our expression that we had. You have this expression here, and you want to use the expressions for del alpha j alpha that you have from this, from this case, and you want to transform the integral from the circle around epsilon, to just its boundary. And now, so what you end up with is the following. So what you end up with is, so your 3.17 essentially breaks up into two separate pieces, one which has a JZ piece, and one which has a J bar Z bar piece. Okay. This has a JZ piece, and this has a J of Z bar piece. So that is what has transpired out here. So the left hand side has changed into this expression. The right hand side, of course, stays the same. So this so far holds for anything in this d equal to 2 case. Okay. Now what we're going to be doing is we are going to be trying to insert things that we have just found. Okay. So let's try and do that. So we are going to use the fact that these are going to be holomorphic and anti-holomorphic. So you remember this, right? You remember it from here. So the fact is that so I showed you this and this, or equivalently, as I said, this is J of Z being equal to TZ epsilon Z, and J of Z bar being equal to 0, because of the fact that the G, the only thing that is not non-zero is the GZZ bar piece, right? Okay, so now we use the fact that this is holomorphic, and then what we end up with is an expression of the form. So now let's try and see this. Let's try and just look at what this is. So if you have something like an integral over closed loop of something which is JZ of Z and O at say sigma 1, and if you are trying to look at what this integral is going to is going to give you, this is just contour integral, right? So this is going to pick up what the residue of this is. So this and this there is a sign out here just because of the way I've chosen to close the contour. So the upshot essentially is that this sort of an integral out here is going to pick up the residue of JZ with O1. And what is this? This is also the residue of the OP between these two particular operators. Remember, when I took two operators and O1 and O2 to be close to each other, I'm going to get a slew of things, and I mean amongst these there are going to be all sorts of things, right? There are going to be singular pieces, and one of the singular pieces goes like I mean z minus omega. So this integral that you have out here is going to pick out the piece in the OP which looks like this, right? So this is we have a very nice way of rewriting this word identity. So if we treat z and z bar as independent, the word identity then splits up into an holomorphic and an anti-holomorphic piece. For example, if you look at del z equal to epsilon z, then what happens is a change O1 is going to be the residue of jz with this is going to be O1. I'm sorry, this is O1 at sigma 1. So this is just again. So this is just so this is ones here as well. Let's put another one out here. And remember what JZ was? JZ, as we just saw, it was going to be, epsilon Z into TZ. So what we get at the end of the day is that O1 is just the residue of epsilon Z TZ and O1. So this change is going to be something which looks like this. Okay. So now, and similarly, you have a similar piece for if you look at del z is epsilon bar z bar. So the upshot of this is that if we know the OP between an operator and the stress tensor, we will then know how these operators will transform under these. The transformation under conformal transformations is going to be fixed, right? And if we flip this around, if in a sense we know how the operator is going to change, then we know some part of its OP with T and T bar. Okay. So what have we done in this section, if you wish, is that we have related the OP. So we had these two ideas to start off with. One of them was the OP, and one of them was the word identity. And I showed you here that by using the form of the OP, you can arrive at the word at the word identity. And also, in a similar way, so what we can do is we can also use how a particular operator is going to, if we know how an operator is going to transform, we can sort of try and figure out at least pieces of its OP with T and T bar. Okay, this was important, and maybe these sort of tricks are something that few of you are seeing for the first time. So if you have any questions, please feel free to stop me, okay? We will try and illustrate this a little bit more. So hopefully things will be clearer as we try and move ahead. But yeah, if you have something more to ask, please do. All right, seems people have understood, or I'm going very fast and people have not understood anything. So all right, let's try and understand this with a few try and see what to do. So what we are going to be trying to do next is we are going to be trying to construct this OP from symmetry, conformal symmetry. So as I said, the word identity will allow us to piece together some OPs by looking at how these operators are going to transform under these symmetries. Let's start off with the two simplest examples, okay? So if we have translations, so del z equal to epsilon, which is a constant, then you can just expand this out And so what is going to happen is O at Z minus epsilon is going to be O at Z minus epsilon del Z, del of O, okay? Now, so this is going to be, so now what has happened is that this is what is the, what the change is, right? So the word identity, the form of this is just simply saying, so remember what the word identity was. Let's just go back to figure out what the word identity was. So the change is going to be minus time minus of this guy, right? So now we know what this is. We know that this is going to be something which is, epsilon. So okay, so here for translations, let's just write this down. So for translations, so delta O1 is going to be equal to what is it again? Epsilon times del of O1, right? This is what we find. So this is going to be equal to, so this, and so this is what is the left hand side. The right hand side is minus residue of, now epsilon is fixed, so that's tz and O1 sigma 1. So this just goes out, so this is equal to minus epsilon residue of t with O, right? So this is what we have found, right? So this means that the residue of T with O is just delta of O1. Okay? Hopefully that is clear. If not, please ask. So you see that, so this is going to be, so that means that T of Z with O of, omega and omega bar, the piece that is going to go like 1 over z minus omega has to be this. Okay? Similarly, for T of Z being, this is T bar, I'm sorry, T bar. Okay, so is 3.22 clear to everybody? If not, please ask. Hopefully this is, is everybody around? It's a very deathly silence around, it seems. This is a little harder than some of the things that we have done so far. But if there is something that you guys want to ask me, please do that. Is this reasonably clear? Is there something that you want me to repeat? All right. So it's either one of two things. Either it's all very clear, or it's all so confusing that everybody's lost. So here's hoping that it's the first thing and not the second one. So okay, so now what we have done is we have used translational invariance to fix the form of the T and TOOP to have something like this. Okay, can we do some more? So let's look at rotations and scaling. So we are going to have Z going to epsilon, Z plus epsilon Z. So this describes rotations when epsilon is purely imaginary, and dilatations when epsilon is real. Now remember that all operators do not have nice transformations under, do not have nice transformations under these, well, nice properties under these transformations. Nice transformations under these transformations is not a very good thing to write. Nice. properties under these transformative. This is, as I write out here, similar to this statement that all states do not transform nicely under the Hamiltonian or angular momentum if you're looking at uh, your usual sort of quantum mechanics. But however, we can choose a basis, right? We can choose a basis, and we can choose this basis to be eigenstates of H and L. And we can describe the Hilbert space with that basis, right? So this is something that's something that you guys know. And this is very similar for the case of CFTs, where we can choose a basis of local operators that have good transformations under rotations and this D operator. Interestingly enough, as we will see in the next few classes, this also will follow from a statement about the states, and it's actually to do with the fact that HR is equal to 0. Right. Now weights, okay? So this is something that we have done earlier. We're just repeating it in another language. So an operator O is supposed to have a weight H bar if under Z goes to, Z, delta Z is equal to epsilon Z and delta Z bar is equal to epsilon bar Z bar, this O transforms in the following way, okay? Now, this term would always be there. Because this just comes by, expanding out, O of Z minus epsilon Z and Z bar minus epsilon Z bar. So these terms are always there. What is new are these terms H and H bar, okay? So these are because they are eigenstates of the dilatations and the rotations, basically. Now, what are we going to do? We are going to take this and we are going to look at the Ward identity as well. Okay. For rotations and scalings which come with Z goes to epsilon Z, Jz is just Z times T of Z, right? So this is, just look at 319, which is what we were doing before. So Jz was this guy, right? So it's eternally confusing to try to see this, but let me just write that this is actually J of Z, and this is J of Z bar. So let me just write these two things down for you. So Jz when epsilon. So what I'm trying to say is when epsilon Z is equal to epsilon into Z. So we are trying to write it, but when it is this, then J of Z is just epsilon times T of Z into T of Z into Z. Okay. So this is the piece which is going to account for translations and this is the piece which is going to account for rotations and scalings. So this is the piece that we are interested in. Now what is happening? We go back to the OPE again. So now what we have to do is we have to, and this is what I said. So as I said here, J of Z is Z times T of Z. This means that when you're looking at the residue of the JO-OPE, this is going to determine the Z squared term in the T. Sorry, let me restate this. When you are looking at the JO-OPE, this is going to determine the 1 over Z squared term in the TO-OPE, because you have an extra factor of Z out here, right? Similar arguments will hold for, so you see that this term, so if you are just looking at yeah, so let's just write this down. So what is happening is if you look at the if you plug this back into the Ward identity again, So what do you want to do now? You want to plug this whole guy into the ward identity that you have. So the ward identity is, as you as you remember, this is what your ward identity is, and you plug in the form of delta O1 on this side, and you and what you want to do is you want to read off this, right? And you have to remember that in this case, epsilon z is epsilon into z. Okay, so once you do that, it determines not it determines for you what the 1 over z squared piece is. Okay, so if you finally what you get is that if you have an OP of an operator O of omega omega bar with weights h and h bar, the form of this is going to be, this is going to be the form. Okay, so you see that this particular thing was determined by translational invariance before. Now you have also got this piece, and as you saw that this was the piece that was that is going to determine the 1 over z squared piece, right? Because what happens is that j of z is epsilon into z times tz. So this is what since so the JOOPE is the residue of the JOOPE in terms of the TOOP will be shifted by one term, so it's the 1 over z squared term. Okay, so what have we done? We have then determined that if we are looking at operators which if we are looking at translational invariance, and if we are looking at things that have a nice weight according to the definitions that we have just given, then the conformal symmetry determines for you what at least some part of the T OP of T with these O's. Okay, and this is going to be the form of them. Okay, now we are going to define a class of operators called primary operators. What are these? These are operators for which the OP with T and T bar will truncate at this at this order. So it'll go from here. Okay, these terms, the higher order terms, will not be there. So this is what I have written in the box out here. So if T of Z with O of omega and omega bar will be of the form that I've just given. So 3.24 determines, if you wish, what your primary operators would be. Now that we know all the singularities of the TOOP, we can reconstruct the transformations of O under all conformal transformations. For example, if you look at del Z is equal to epsilon Z, this is just going to be the what the residue of this guy is. So you plug in the OPE, and you expand, if you wish, epsilon Z in this way. So then you see that the infinitesimal change in the primary operator is of a form like this. Okay, and analogous relation holds for dz bar is equal to epsilon bar z bar. Notice that 3.25. You could say that what you're doing is sort of going around in circles, but I wanted, you could say that we have already assumed something like this to get to this form, but let me just assure you that that is not quite the case. And what we did earlier was we assumed something like this. Okay, so the form that we had was something like this. If this were to transform nicely under this dilatation and rotations, then we just labeled it by h and h bar. Right now we are doing it for this whole, whole infinite class of conformal transformations. Then we see that the change in the operator is of a form like this, and an analogous thing also holds for z bars. So at the end of the day, what you can do, you can integrate. So this was the infinitesimal form. You can now integrate it to find what the finite form was, and the finite form is going to be given by 3.26. And as you can well understand, that this was all a rewriting of what we had previously defined. So as I write out here, and again, you must have noticed, is that the forms that we defined out here, this one and the infinitesimal form here, are things that you have already seen earlier, right? When we defined these things earlier, you have already seen this. So let me just take you back to that once quickly. So we defined, if you remember that, you defined the transformation of, okay, not here. So we defined, if a field transforms under conformal transformations as this 3.12, we defined it as a primary field of h and h bar. You have seen the same things in terms of an operator language now. You have reconstructed it, if you wish, out of an OPE, okay? So, right. Okay, so that is what I wanted to do. So one of the main objects of interest in a CFT is the spectrum of weights of the primary fields, h and h bar. This is sort of like an equivalent of computing the mass spectrum of a field theory, or in StatMech, the weight of these primaries will actually turn out to be the critical exponents which rule phase transitions. So okay, so that's what I wanted to do for this class. I don't want to go into the free boson now, but now is going to be a good time to pause and ask you if you are fine with what I did in the class, or if you are uncomfortable with something, if you want me to repeat something, and so on. And deathly silence follows. So is everybody fine with what we did in the class? Are you guys okay with that? Should I be asking you guys individually?
I have a question.
Yes, please.
So like deriving these the general OP structure, like you didn't assume that anywhere this operator O is a primary operator, right?
No.
But just like by the symmetries, like how it transforms under translation, rotation, and dilatation, you get this form. And there
Yeah,
are other terms as well.
I get this form.
Yes.
Right.
Right.
But notice that there are these dots here, right?
Right. Yes.
So these are the dots that I do not know about.
Right.
These will be the sort of singular pieces which might be there for other operators, right? Now we are
Right.
defining a special class of operators for which these dots are not there. Yeah, so our primary operators will be defined by just this.
Right.
And not these guys anymore. That's all.
Yeah, okay. But like if you had just started with the primary operator, you will just get 3.24 if you run the same proof. Like
if you we okay, so let's do this. So if you were to understand, if you were to try and determine what the OP of primary operators were, so if you sort of, I mean, assumed this, right?
Right. Yes.
Or
Yeah.
if you I mean, assumed this, in that case, if you ran it backwards, as you rightly say, you would end up with this. So
Right.
what I did here is I assumed another way to start off things, look at ward identities and fix up some of the things and so on and so forth. Then your the TO OPs would be of a form like this. And then I said, I'm going to define a special class of operators for which these are not there. And if these are not there, this is how I'm going to, I mean, how I have defined my sort of primary operators of h, weight h, and h bar. Then we see at the end of the day that if you do this, then what we end up with is the same that we had said at first, right? So it's sort of the same way to get at. So you can either use symmetries to get at the I mean, OPs, or you can use the OPs to get at the symmetries.
Yes,
Okay.
Yeah. Okay. Yeah, thank you.
Sure. Okay, so any more questions?
No.
There seems to be some feedback from somewhere, but okay. All right. So what we will do is okay. So we will look at an example from, I mean, next time around, and we are going to do try and make this a little more clear and concrete from next time around. And yeah, so that's about it. We will see this more from next class. Okay, guys, then let's meet again day after tomorrow. All right.